documents, the ones that count towards your final grade, are due down here. If you've forgotten your rubric, you might want to run out and print one. If somebody is so inclined, they can go and print out 10 rubrics and then start selling them in the back if they want to. And also remember that assignment 7 is due on Friday. That's your last part of the major project. That's due tomorrow in a little more than 24 hours. And then finally, your assignment 8 or your bonus, if you're so inclined to do that, would be due by next week. So assignment 8 is going to be due in class because it's all written up. There's no electronic submission. You have to actually hand it in class. And so we'll be expecting that on Thursday. Moreover, if you are doing the bonus where you want 50% of your points back on a particular assignment, you need to be meeting with your LA very, very soon, because they will only be here up through and including dead week, whoever graded it. If you're going for that 100-point bonus, that is also due next Friday at midnight, and that is an electronic submission because it's all it's mostly programming. There is a write-up portion to it that's also due. If you are trying to do that, then go ahead and email me, and we'll work something out there. So today we're going to finish up on looking at heaps and finish up trees and tree-based data structures. We started looking at the properties of a heap and what a heap was last time. Remember that it has two basic properties. It's fullness properties. That means that every node is present except for possibly the last row. And in the last row or the last level, everything is present to the left. So you don't have a situation where you have a gap. Say that we had this right child on 40. Well, we have a gap here and a gap here. That is not a heap, right? That does not satisfy the fullness property. So that's the fullness property, as we observed last time. It guarantees that the depth is going to be order log n. And if we can get our basic operations to be proportional to the depth, that means that all of our operations are going to be efficient, unlike a binary search tree or a general binary search tree. The second property is that keys and nodes are less than both of its children, right? That's why we call it a min heap. You can flip this and say greater than both of its children, and then you'd get a max heap. But in practice, it doesn't really matter because you would build a heap based on a comparator. And if you want to go from a min to a max comparator, all you need to do is flip the sign. So there's generally only one implementation. You either go with a min heap, a max heap, or a generic heap using a comparator. But this property guarantees that where's the minimum value in a heap? It's always going to be at the root. So this suggests that we can do two things. One, we're going to have a general insert method, insert operation. And remember, when we described the heap, when you put something on top of the heap, you don't necessarily get to tell where it ends up. It could end up on top of the heap. It could trickle down to somewhere inside the heap. It could trickle down all the way to the end of the heap or something like that. So we don't get to arbitrarily do whatever we want. Just like a stack, you can't arbitrarily pull something out from the middle or access something in the middle without losing the efficiency of the stack. You can't do that with a heap either. You can't do a linear. You can do a linear search if you want to, using a pre-order, post-order, or in-order traversal, but then that's linear, right? And then the second operation that we're going to support is get and remove the minimum element. Well, getting it is kind of trivial because if you just want to get it, then it's right there. And that's the very first element that you get. But what we want to do is get and remove it. Okay? So we're going to focus on the second one first, and then we're going to discuss how it works. And we're also going to write some pseudocode, maybe, depending on how much time we have. So let's go ahead and get and remove the element. So I'm going to outline what we want to do. We want to save the root element off to be returned, be output or returned. I'll go ahead and use the term returned here because it's closer to what you would actually do in code. So this element is no longer here. We've saved it off. 10 is over here. What do we do now? Well, if I just cover this up, is this a heap anymore? Nope. So if I delete this, I need to fix the heap somehow. Okay? What's one obvious thing that we could do? We no longer have a root. We need a new root. So what could I do? I could look at its children, right, and say, which one of these could be promoted up so that I don't, I'm keeping this fullness property here. Could I promote 20 up here? This is 15, by the way. No, why? Because then this would violate the heap property right here. So let me go ahead and promote 15 up. I'll go ahead and move 15 up. Right? Now I've got another problem. Now I've got a gap there. So I need to fix this problem. How? Well, if I take the same strategy here, I'll go ahead and promote up the minimum. And so now 40 is here. Well, now that's gone. Is this a heap, though? No, why? We've got a gap right here. Remember the fullness property. Everything has to be present up until the last one. And the last level, it's all full and to the left. So let me go ahead and rethink this. Okay? Let's create a new heap here, or the same heap maybe. 10, 20, what was it before? 15. There we go. 50 and 25 and 70 and 60 hanging off of 50. Come back over here and what was it before? 40 and 80. Okay, there's my heap from before. Okay, and let me go ahead and turn this down so there's not much of a glare. There, that's a little bit better now. Right? I'm doing pencil here because I want to be changing this stuff, and so I want to be able to erase it. So let's go ahead and do the same thing that we did before. One will save the root. Right? And so I'll go ahead and save the root off over here in some temporary variable, 10. And so then we'll go ahead and return that. Now, I got into trouble here by promoting the children immediately because I wanted to preserve that heap property and the fullness property. Let's not think about the children. Let's think about some other node that we could promote up here so that the fullness property is satisfied. The heap property might not be satisfied yet, but we can take care of that later. We got into trouble with promoting the children. I don't want to get into that trouble again. What could we promote here in order to preserve the fullness property? I could put the very last one, the thing at the lowest level, all the way to the right. I could promote that up here. And when I do that, well, it has no children because it was the last one, so we can get rid of it. Right? Now, the fullness property is satisfied. So promote the last node to the root. Right? And that preserves the fullness property. But is this a heap? Is it a min heap, I mean? No, 60 is not less than both of its children. Now we can do what we did before. We can go through and say promote the minimum. Right? So I'll go ahead and swap these two. 15 comes up here, and 60 goes down here. Now, with respect to just these two levels, it is a min heap. So, but with respect to these levels, is it a min heap? No. We still have to keep going. So I'll go ahead and swap it with the minimum of its two children. Again. And 40 comes up here, 60 goes down there. Now is it a heap, a min heap? Yes. Everything, every node has its key is less than both of its children, and we didn't touch anything over here, so that was perfectly fine. So all we need to do is exchange or swap the new root downward into the heap until the heap property is satisfied. So that's the general outline there, right? We're going to write some pseudocode here to codify that, and then of course the final thing that you would do would be output or return this temporary variable here. But before I do that, I want to observe at most how many swaps would you have to do? I only had to do one comparison and one swap, one comparison and one swap, right? I assumed that I would have access to this last one. Remember, you always have access to the root because that's how you design a tree. I'm kind of leaving this as a mystery for now. How do you have access to the last one? And we'll see that it becomes apparent when you see how these things are actually implemented. So just assume for now that you have access to the root for free, that you have access to the last element for free. Swapping them is a constant operation. But this operation right here, you might have to swap it all the way down into the heap until it gets to the bottom of the heap. Right? Remember, when you put something on top of the heap, you have no control over where it ends up. It could end up as staying at the root. If I inserted one, or if I, this is getting them in right now, but it could end up staying at the root. It could end up somewhere inside the heap. It could end up at the bottom. Right? You don't really have control over that. That's entirely dependent on how the heap was built prior to this. Okay? So we'll swap the new root down. How long will that take? How many comparisons would you have to do at most? So observation. There are at most being worst case complexity, D, comparisons, or swaps. In other words, the get and remove min is going to be order D. Remember, at worst case scenario, that's what big O analysis. And because of the fullness property that we observed before, this means that it's going to be order log n. Because it's always full, the depth of this tree is always going to be order log n. Right? Great, we've achieved one of our goals here of a get and remove minimum element. That's going to be efficient. But now we need to understand how we end up doing this and eventually how we actually implement this, this heap. So let me go ahead and write some pseudocode here. My input is going to be a heap, H, with an appropriate root, right, and a last element. And what we're going to do is we're going to output the removed minimum element. Okay? So, first thing we're going to do, again, I outlined it over here. Right? We're going to save off the root, h.root, element, item, value, whatever you want, right? So that we can output it later. Then I'm going to promote the last element. So what I'm going to do is I'm going to say that h's root becomes h's last, right? And delete the last node, right? So all we're doing is swapping those nodes. That's, again, a constant time operation, okay? Now, what I want to do is I want to swap the new root downward into the heap until this heap property is satisfied. When is this heap property satisfied? Suppose it looks like this. Suppose I'm looking at this key and it's 40, 60, 80. Is the heap property satisfied? Yes. Why? Because the key in the current node that I'm looking at is less than the left, and it is less than the right. So that's one of my stopping conditions, right? One of my stopping conditions is when I got a key in the current node, if it's less than both of its children, then you stop. Flip that. How do you keep going? While that's not true, while this is greater than or equal to, or there's no equal to there, sorry. While this is greater than its left child, or it's greater than its right child, that means that you need to flip them around. All right? So we're going to go into a while loop here. While. It gives myself some room here to figure out some variables. While the current node's key is greater than its current node's left child key, right? Or the current node's key is greater than the current node's right child key, right? Unfortunately, I fell off the page there. Then I will need to keep going. I will need to swap it with one of its children. So I'm going to put that into a comment here. Swap the current key with the minimum child. And for that, I just need two if conditions, right? If I need to determine, was it this one that got me in here, or was it this one that got me in here? And frankly, it doesn't matter, right? It doesn't matter if you do this one, or you favor the left or favor the right. There is no, sorry, we're not allowing duplicates, so it's going to be one or the other, not both, right? So if the current key, current dot left child is dot key, is less than the current's right child key, right, then that means that this is the minimum, and that's the one that we need to exchange it with. So I'll put in here swap current dot and current dot left child. And what I mean by that, I mean their keys / values. We don't actually need to change any references. The parent reference, the left child, the right child, those can all stay the same. But we do need to swap out the contents like I did with this example here. I didn't redraw these nodes. I just erased what was inside of them and swapped those instead. Right? Else, and this is the other condition, current node dot left child dot key. And this is not necessary to put in this condition here because it's either or, is greater than the current node's right child key. But I'm putting this in here for presentation purposes. We'll swap the current and the current dot left child. Okay? And that's it. Okay? Is that our only stopping condition, by the way? So let me go back to this example. What did we do? 15 was swapped with 40. 40 went down. 40 was swapped with 60. I guess it was 60. 60 came in. 60 went down. 60 went down. Did 60 go down any further? So what's another stopping condition that we need to consider? So why did we stop here at 60? It has no children, right? There's no child to swap it with the left. There's no child to swap it with the right. Right? So what I'm going to put in is another stopping condition here. And unfortunately, I didn't leave myself enough room on this. I forgot. While this or no children, and I guess, and it has both one or two children, then I'll go ahead and continue. Right? Otherwise, once I'm out of this loop, I can output the value that I saved off here, and now I need to initialize my current. Where does my current start, by the way? Where did you start over here? I started at the root, right? So h.root. Okay? And there's the remove the minimum and replace it with the last, and then make sure to fix the heap, put it down. Sometimes this algorithm is called fix heap. Sometimes it's called heapify, but whatever you want to call it. All right, well, that's one operation. What about the other operation? And this one I'll just outline. The other operation is insert. Right? So again, let's go ahead and go back to this. And suppose that I wanted to insert, I don't know, 1. Let's insert 1. Again, if I take the strategy of trying to start at the root here, and I insert 1, what am I going to end up doing? Well, 15 has to go somewhere, so it's got to be pushed out, right? So maybe 1 takes over here. Well, where would 15 go? Would it go left or would it go right? I don't know. Let's say that it goes right. Now 40 has to go somewhere. Well, it gets pushed out, pushed down. Maybe it gets pushed down over here to the left instead. Well, 60, you didn't want to lose that, so where does that get pushed down? Over here? Right? What happened, though? Is that a heap? No. So again, we need to take the strategy of preserving the fullness property first. All right? One, we insert the new node / key at the last possible place, right? This is the last level all the way to the left. Right? So pictorially, what that would look like is, if I wanted to insert one, I wouldn't start at the root. I would go to the last one right here and insert it right there. Now, is that a min heap right there? Nope, because now this new child is less than its parent. So we can take the same strategy. What would we end up doing? We would end up heapifying upward instead. I would end up swapping these, swapping these, swapping these, and one would end up as the new root. Right? So it's the same basic idea, except that instead of starting at the root and heapifying it down, you start at the last and then you heapify it up. Right? So you insert the new node as the last possible place, the last level, all the way to the left. Then you fix the heap by comparing it to its parent and swapping until it is greater than its parent. Or, what's the other stopping condition? If I inserted, like, I don't know, if I inserted, let's say 30. I don't know if 30 is in here already, but if I inserted 30, I would end up swapping it with 50 to fix it. But I would end up not swapping it with 20 because 30 right here would be greater than 20, and so you don't need to swap anymore. You didn't go all the way up to the root. But the condition that I did here, 1, I ended up having to swap that all the way up to the root. So what's my other stopping condition? Or the current node is the root. Right? So same basic idea, except it's going from the bottom of the heap up to the top of the heap. And again, it's the same analysis here. That you start at the bottom, you go all the way to the top. Well, if you have to do so many swaps, so many comparisons, you're only going to do order D comparisons. Order D swaps or comparisons. And because of the fullness property, order D is going to be order log n. All right? Great. We've got a restricted access data structure. Remember, it's kind of like a stack or a queue in that you can't arbitrarily insert stuff, arbitrarily search for stuff, arbitrarily delete stuff. You can only do an insert, which you have no control over, or you can do a get min. You can't just get anything that you want, efficiently at least. So we've got a restricted access data structure that is efficient in both of its core operations. Right? How can we use it? Well, how can we implement it first? Right? Then we'll talk about applications. Right? So, implementation. Here's the dirty little secret. It's actually not a tree. Right? The most common, the most easy way to implement this is with a plain old array. Right? Let me go ahead and go back to the original here. It looks something like this. 10, 20, let's say 15, I don't know. And then I can't read my writing anymore because it's all crossed out, so 70, 80, it doesn't matter. You can just make up new numbers here. 50, 25, and then 70, I already did 70, so 75 and 60. There we go. There's my heap. All right? It was built somehow, I don't know. This is not actually how it's usually represented. Instead, it's all stored in an array. Right? What I'm going to do is I'm going to draw this array, and then we're going to figure out how it works. Make sure if I get more. So here's the index, and here's the key. Right? What I'm going to do is I'm going to burn that first one. I'm not going to use 0. Right? it's not that big of a deal. If you really, if you're really, bothered by burning this one element, you can fix it in the end. You just have to subtract 1 off of everything. But what I'm going to do is I'm going to do a traversal here. I'm going to go 10, 20, 25, 50. I did 25 here. No, this was 15, sorry. So 10, 20, 15, 50, 25, 70, 80. I said 75, but it's 70, 75, and 60. There. I gave myself enough room. Good. Right. I wrote small enough at least. Right. So these are all the indices. 2, 3, 4, 5, 6, 7, 8, 9. And then, of course, you've got room to grow over here. Okay? Great. What kind of traversal did I just do? I went left to right, top to bottom. Remember what kind of traversal of a tree that was? Does anybody remember? It's certainly not a pre-order traversal. Pre-order traversal would have been 10, 20, 50. It would have gone deep. This one went shallow, right? It went breadth first search. So this is a breadth first search, top to bottom, left to right traversal of this tree right here. Now, why does this work out to the same tree over here? So tell me what the index for 20 is. So key is 20. What index is it stored at? 2. Right? Its left child is stored at what index? 50 is stored at 4. And its right index, or right child, 25, is stored where? 5. Right? Let's look at another example here. Let's look at 50. The key 50 is stored in the index 4. Its left child, 75, is stored at index 8. And its right child, 60, is stored at index 9. Do you see a pattern emerging here? Right? If something is stored, if there's a key, say k, stored at index I, where is its left child? 2i. Right? Where is its right child? 2i plus 1, right next to it. Where is its parent? So I didn't do that up here. Where's 20's parent? It's at 0, right? So where's 50's parent? 50 was right here. 50 is at index 4, and its parent 20 is at index 2. So how do you reverse this? I divided by 2, and you have to work out for both left child and right child. So what about 15? 15 is at index 3, so 3 divided by 2 would give you 1.5, but its parent is at 1, so what kind of an operation would give that to me? It would work out in both cases. You take the floor. All right? It's pretty cool, huh? All you need to do is, if I'm at index I can jump to its parent using random access by going I divided by 2, floor it. And if I want to go left, all I have to do is 2i. And if I want to go right, all I have to do is 2i plus 1. Right? And it really works out really well here because you can use all the utilities that you know everything about with an array, but you can get a tree implementation out of this. And this only works for heaps. If you had huge gaps here, for example, if I didn't have a right child at all, right, or say I didn't have a left child at all, there would be a huge gap here where there would be no elements. And you could potentially have this exponentially sized array. There's this big, huge exponentially sized gap that you now have to jump to get to the actual children, right? The right tree. And so if it's not a heap, if it's not full, you actually don't want to use this kind of an implementation. The only reason that we can use this kind of an implementation where all the array elements are all contiguous is because of this fullness property of the heap over here. Right? Pretty cool. Now all you have to do to, let's say, where were we here? Where's my pseudocode is what I want. So all you have to do is translate this stuff to indices. If I want to, one thing I forgot here is then go left, all right, or go right, all right. When I say go left, all I mean is keep an index. Instead of keeping a current node, you would keep a current index, I. And to go left, all you would do is go I times equals 2, right? Double it. All you would do to go right is multiply it by 2 and add 1. If you ever actually need to go up to the parent, for example, in the insert, where we went from the bottom all the way up, you can do the parent as well. All you have to do is take and divide by 2. And if you're in most programming languages, then you don't even have to take the floor, because truncation will take care of it for you. Right? 3 divided by 2 is just 1, because it's 2 integer values. Right? So really, really nice implementation here using an array. Right? And again, you have to burn this for this to work out. If you don't like burning this, that's fine. All you need to do is -1, -1, -1 everywhere, right? And then you're shifting everything down over here. Okay? All right. Great. I will note here that if you want to, you can use nodes. All right. Observations. Let's go with observations. All right. Well, first of all, with an array-based implementation. Do we have access to the things that we need? For example, where's the root located? Where's the root always going to be located? It's at index 1, right? Unless you want to shift it, right? Where is the last element? Remember I said that I'm going to hand wave it for now and say, well, you have free access to the last one. Where's the last one going to be? At what index? Where was the last one here? 60 was at index 9. Why? How many elements are in here? 9. So it'll be at the index equal to the size. That is the number of elements in the array. So it's kind of like our array-based implementation of a list data structure. We created an array that was, say, of size 10. Even though we didn't have 10 elements in there, right? We had a capacity 10. But we kept track of the size so that we could always append something to the end for free. And it's the same idea here. You keep, as a consequence, for efficiency, you need to keep track of the heap size. And that's really easy, right? Anytime you insert something, you increment it. Anytime that you remove something, you decrement it. Okay? All right. You can efficiently implement a heap with binary tree nodes. If you're interested in how it works, hopefully you've read the book, the required reading, because I go through the math of basically the problem is if you've got this big giant heap, you need to know where the last element is. And so if you start at the root node because you don't have free access to the last element, you need to know where that is, or where the next to last element, the last element is, or the next gap over is. And both of these have the same algorithm. If you start at the node, all you need to do is answer the question at the root node. All you need to do is answer the question: is the last element in the left subtree, or is it in the right subtree? And if you can answer that question, then you can, okay, well, if it's in the right subtree, let's go down to the right subtree. And you answer that question again. And you answer that question again, go down into the tree, order log n because it's ordered depth, and you can answer this question all the way down to find the last element. And all it is doing some very, very simple geometric series math. Remember, on Tuesday last week, when we motivated why we want to look at binary trees, is because if you add up the powers of 2, I running from 0 up to, say, d, then this is equal to 2 to the d plus 1 minus 1. right? It's extremely regular. So all you need to do is compute, well, how many nodes are there, right? And how many nodes would there be if it's full? And then that tells you, well, if it's less than this or if it's greater than that, then it's in the left subtree or if it's in the right subtree. And you can just keep going down and applying this math all the way down, right? Really, really nice, elegant solution, except for the fact that the matter is that to find the last element, it's no longer free, right? You can't just jump to it because of random access. Finding the last element would be order log n, right? So you are paying, again, you're paying twice for the same thing, but it is possible to do it efficiently, right? But the vast majority of implementations I've seen are always going to be an array-based implementation. This is a little bit more error-prone because it requires that you get the math right. Whereas an array-based implementation, everybody knows how to use an array. Everybody knows that you can go how to multiply and add, right? This is a no-brainer for simplicity right here. And if you are if you're designing thing, remember the KISS principle, right? Keep it simple, right? Stupid, right? Although I usually try to leave off that last S. I don't know how to pronounce KIS though. Right? All right. So applications. So remember that you have access to two efficient operations. It's a collection data structure. You can put stuff in efficiently. You can take out the minimum element efficiently. Or if you want to flip that around, the maximum element efficiently. How could we use that? What other data structure have we looked at? Say queue is very similar to a queue, but instead of first in, first out, it was had a VIP service, right? It had a very important element service. That the first one in was not the first one out. Instead, you had line jumpers, people that could jump to the head of the line because they had a higher priority, right? Remember priority queues, right? Where when you insert something, it has a priority, right? And when we did this with a list, well, we looked at it, well, it has a higher priority here, higher priority here, higher priority here. Oh, it has a lower priority than this guy, so that's where they belong, right? We inserted it where it needs to be, which is what you're probably doing for your last assignment here, right? And it's perfectly fine to do it. You don't need to use a heap. You don't need to use a binary search tree. We're not looking for those, although those would be more efficient options. A priority queue, doing that, checking every single element to see where it needs to be, that's order n if you do it with a list or a linked list. But a priority queue of nq, right? This is going to be order log n with a heap. Because there's no special thing that you need to do. An nq operation is basically an insert operation. Right? That's it. You're just inserting it into the queue. Right? But what about a dequeue operation? This is also going to be order log n. Why? With a heap. Because all it is get and remove the minimum. The thing with the highest priority, the minimum value. Again, if you want to think of it as higher numbers have a higher priority, all you need to do is flip it and do a max queue instead. It's get and return the minimum element, or get and remove the minimum element, which again is going to be order log n. If you did this with a plain old array-based list, array or linked list, one of the other of these operations is going to be inefficient. To enqueue, it would end up being order n. If you end up having to start at one end and saying bigger, 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 okay, here's where it needs to be, right? You could use binary search to say that, oh, it's bigger, it belongs over here in the upper half of the list, or belongs over here in the lower half of the list. Jump there, find where it needs to be. That'll be order log n. But if you're doing that with binary search, that means that you've got an array-based list, which means that if you want to put it in the center here, what do you have to do? You have to shift everything down, which again is going to be order n. The dequeue operation here, of course, would be, possibly if you're using a linked list, that's going to be efficient. If you're using an array-based list and this is the head of your queue over here, you can go ahead and take things off efficiently there. But one of the other things of these operations is going to be efficient for one of the other list implementations. Whereas over here, they're both going to be efficient log n. And you might think, well, wait a second, this is more efficient, right? And it is. This constant time algorithm is much better than a logarithmic time algorithm. But if you're going to put stuff in, you're eventually going to have to take stuff out, right? So if you put stuff in and then take it out, it doesn't matter if one of those operations is free. You still had to pay up front for that first operation. Order n plus order 1 is going to be order n. Right? If I add these together, you can look at it as order n. Whereas if I add these two things together, what do I get? I get 2 log n, which is still going to be order log n. So you're paying up front and then getting something free later on. It doesn't matter. Over here, you're paying a little far less up front. You're paying a little bit more on the back end, but it's the same amount, right? So no matter what, a heap implementation of a priority queue is going to be a lot better than a linked list or an array list. Okay? Here's another application. So if I've got this bucket, that's the queue, I'm going to just throw stuff into it. I've got 10 elements. Throw everything into it. Start taking them out one by one. What order are they going to be in? Let me go back to this right here. If I start taking these out one by one, I take out 10, and then it gets fixed, 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 fixed. What ends up at the root? 15. I take that out. Fixed, 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 fixed. What's the next thing to come out after 10 and 15 are gone? 20. Take that out. Fix, 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 fix. Right? What's the next thing that comes out? 25. 10, 15, 20, 25, blah, blah, blah. Go all the way to the end. What am I doing here? What have I ended up doing? If I throw everything into this big giant bucket and then start dumping them out one by one, it's all sorted. Heap sort. Extremely efficient code here, or extremely simple code. Let's go ahead and write it. My input is going to be a collection of elements, A1 through AN. Right? My output is going to be A sorted. Right? All I'm going to do is initialize a new min heap. Right? All I'm going to do now is put stuff in. For each A in A, H dot insert A. Right? And now all I'm going to do is take stuff out. Right? So I'll create a new collection here. I don't know. Here, I'll do it this way. For each, for I running from 1 up to n, what I'm going to do is I'm going to assign a sub I to be h dot get min. That's it. I'm running I from 1 up to n, so it's going to be reordered. I'm going to get the minimum first, then a sub 1, a sub 2, a sub 3, etc. Each time I'm getting a new minimum. Look at that code. Right? What am I doing here? I am putting stuff in. What am I doing here? I'm taking stuff out. Does it get any simpler than that? No, it's just 2 for loops. Put stuff in, take stuff out. Put stuff in, take stuff out. I would characterize this as extremely dumb code. It's just 2 for loops. Right? Where is the real power here? Where's the real smarts? The data structure. Smart data structure. Right? So remember back to one of the themes of this course, Eric S. Raymond. Smart data structures and dumb code are a lot better than the other way around. Smart code, clever code, like say quicksort, clever code where merge sort or something like that. Now, in practice, you have other considerations, but as far as elegance and simplicity, this is dumb code. This is a lot better than trying to figure out, as many of you did in lab 13, where you had to write your own merge sort or quick sort. I forget which one it was, but the vast majority of you just went to the internet, right? And which was perfectly fine. That's what we expected, and pulled somebody's code off. I'll tell you now, though, that there have been studies done on complex algorithms like quicksort, merge sort, et cetera, that 90% of the code out in the wild has some sort of undiagnosed bug. For 15 years, or maybe it was 20 years, Java itself had an undiagnosed bug in its either binary search or in its sorting routine. It went undetected for 15 years. I think it was an overflow bug. It's because getting complex code, getting code with a lot of moving parts, a lot of potential failure points, is extremely hard to get right. Testing can help, but it's still very, very hard. You didn't think anybody ever tested Java's sort method over 15 years? Lots of people tested it, and lots of people failed to find that bug. Right? On the other hand, characterize this code. There are very, very few failure points here. Right? It's really hard to get a for loop wrong. It's really hard to get another for loop wrong. The real power is inside the data structure. And if you have an assurance on the soundness of the implementation of your data structure, that's a lot better than the other way around. Right? So, smart data structures, dumb code. Again, at the end of this course, one of the things that you should be asking yourself is, instead of immediately going and building a top-down solution, is start asking yourself, what kind of data structures would solve this problem for me, or would take care of 90% of this problem for me? Oh, a heap, because I know that it has an efficient way to put stuff in and take out the minimum each time. I'll go ahead and use that. Right? And then you pull it off the shelf, and 90% of your problem is already solved. And it's solved efficiently, and it's solved with a smart data structure. Right? So, before we do that, though, or before we end, let me go ahead and try to analyze this. Okay? So, how many comparisons for heap sort? Remember, it looks great, right? Dumb code, smart data structure. It looks great, but if it's inefficient, well, it doesn't matter how it looks. Right? Throw it out. Right? If we can't beat quicksort, if we can't beat merge sort, then there's really no point in using that. So can we at least match them? Okay. So how many comparisons for heap sort? I'm going to focus on one of the phases. Phase one. Phase one, putting stuff in. What I'm going to do is I'm going to unroll all that entire loop, right? So on iteration 1, the size of the heap is 0, and consequently, how many comparisons do I end up doing? So if I just take the first element and throw it into the heap, its size is 0. Where do you put it? Well, you don't even do any comparisons. You just put it as the new root. Okay? On iteration 2, the size of the heap has now grown because we put in the first element, right? And so the size of the heap is now 1. The number of comparisons is roughly going to be log of 1. Tell me, what is log of 1? 0. So plus 1, right? Forget about that, right? On iteration 3, the size of the heap will be 2, and so we'll have about log, again, about. So I don't want to have to worry about those plus 1s, minus 1s, whatever, right? It's going to be about log 2, which is 1, right? On the 4th iteration, the size of the heap is 3. It'll take about log 3 comparisons, right? Dot, dot, dot. On the ith iteration, how big is the heap? What's the pattern here? I minus 1. So it'll take approximately log of I minus 1 comparisons. Okay? Dot, dot, dot. What's the last iteration that we do? How big was the collection? N. We do this for n iterations. And it'll be n minus 1. And so it'll be log of n minus 1. Okay? All I need to do is add up all of these comparisons to tell you how many comparisons there actually are. So what does that look like? Well, first of all, I'll ignore this. I'll start at 2. Okay? It's going to be a summation of I running from 2 up to n of log of I minus 1. Right? Now, I don't like that minus 1. Does anybody know in a log identity that you can break log of a plus b? Can you break that up? Log of a times b, can be broken up into log a plus log b, but there's really no way that you can break this up. So what I'm going to do is I'm going to make it bigger, just like you're going to do in your last homework assignment, the written homework, where you have to prove big O analysis. You just make it bigger, bigger, bigger until it matches what you want to show on the right-hand side. So I'm going to make it bigger by adding 1 on each one of these things of log of I. All I did was add 1 to each and every single one of these, and I made it bigger, right? Log is a monotone increasing function. If I subtract something off on the inside, then I'm making it smaller, but I can always add 1 to simplify it. Right? Now, what is this? This is equal to log of 2 plus log of 3 plus log of 4 plus log of n. Okay? Plus. Just look at 2 of these here. Off to the side here. Log of a plus log of b. What is that equal to? Log of ab. And you can apply it twice. You can apply it once, twice, thrice, as many times as you want. And this is simply just log of 2 times 3 times 4 times times n. Okay? All these are equalities. This is the only inequality so far. What is this thing on the inside? It's missing the 1, but that's okay because 1 times anything is that thing. So it's going to be log of n factorial. Now, n factorial is huge, remember? It is super exponential. But if you take the logarithm of a super exponential, what do you think happens to it? What happens when you take a logarithm of an exponential? It just becomes like a log of 2 to the n. That cancels the 2 out, and it becomes just n, linear. Something else happens here, right? So I don't want to get into how to actually do this because it would require Stirling's formula. But so I'm just going to come up with an inequality here. Log of n to the n. Right? That's certainly bigger than this, right? Why is that? I've got 2 times 3 times 4, What is the largest term here? Remember, big O analysis, you want to focus on the largest term. What's the largest term here? N. So if I replace 2 with n, which is even bigger, if I replace 3 with n, which is even bigger, if I replace them all with n, I've got n times n times n times n times n, which is equal to n to the n. Right? Now what? Now apply another log identity. What happens when you take log of a to the b? What happens to this b? B goes out front. And so what do you have now? N log n. Sound familiar? Right. This is order n log n. No fancy recursion, no fancy divide and conquer strategies, no in-memory stacks, nothing, right? All just simple code. 2 for loops and a smart data structure, and you've matched the power of those other sorting algorithms, right? The C standard library, at least my BSD implementation, its QSort is actually a call to quicksort, or a call to heap sort, I believe. It has a standard heap sort implementation. It's called heap sort or H-sort. I believe that Python has an H-sort. I'm not sure about that though. But the standard sorting algorithms for for Python and now Java, as of Java 7 or so, is another algorithm called timsort, which is a bottom-up kind of merge sort that looks for long segments of pre-sorted stuff in your collection, and then it uses merge to merge those together. So it's called timsort because of Tim. I don't know what his name is, but he came up with it in Python 10, 15 years ago. But there are implementations of heap sort. What you're actually going to use in practice, that becomes an engineering question. How big are the things that you're sorting? Is it now more important to reduce cache hits or cache misses than other things? Again, an engineering decision might lead you to an inefficient sorting algorithm like shell sort or bubble sort or something like that if you've got other concerns like limited memory. Right? But as far as a theoretical point of view here, no contest in my opinion. The elegance of this algorithm, the dumbness of the code, the smartness of the data structure, and the fact that it is no worse and meets the performance of quicksort, merge sort, that wins in my book. Right? Remember, smart data structures and dumb code are a lot better than the other way around. Right? And what time is it? Okay. Any questions so far? All right, that was basically the capstone of this course. When we come back on so remember next week, when we come back on Tuesday, I will give a short summary of the course so far, and we'll wrap up any loose ends that we might still have out there. On Thursday, I was thinking about switching them, but on Thursday we'll do a review, and the review will simply be like the midterm. I will bring the question bank, multiple choice. We'll do as many as we can, as many as you want. I don't know how many questions there are because I haven't created it yet, but you can bet that there will be questions from pre-midterm stuff, but the vast majority of those questions will be on post-midterm stuff. So let's see, data structures and all list data structures, searching and sorting, algorithms and algorithm analysis, trees and tree-based data structures, all that stuff that's on your final homework, the written homework. But otherwise, also keep in mind next week, I guess tomorrow is the Senior Design Studio Showcase over at NIC. Next week on Wednesday is the CSE Senior Design Showcase in the Union. And so my office hours will be canceled that day, and many other LAs will be canceling their office hours if they're in senior design or design studio. So keep that in mind. And then I think that's all. If there are any other reminders, I'll put them out in the weekly retrospective. But otherwise, see you next week for your final week.